So today was our first day with balancing nuclear equations, and what we went over was I tried to explain to you guys what nuclear chemistry is and why we need to learn about it, and then I went into showing you guys where you could find your stuff. So your notes are here, and these are specifically just for notes, and then there's a key. So what I'm going to work on today is just a couple examples in the notes, and then of course you can check the key to see how you did. And then the videos are here, and these videos by Tyler DeWitt are really good. They'll actually go step by step again in the process to make sure that it's understandable for what you're supposed to be doing. And again, this is in week 8. And then the actual assignment that you're supposed to be doing is the balancing nuclear equations for Tuesday, which is today. So balancing nuclear equations is the actual assignment. And then the notes are here, which is what I was just showing you, and then videos that go along with it. So if you click on the notes, they look like, if you click that, they look like this. And we went ahead in class and already went over them. So the answers are already here, but I can go ahead and delete those later if you want me to. We also discussed the different types of radiation, and the different types of radiation are your alpha, your beta, and your gamma. Alpha being the slowest moving and least penetrating, going all the way down to gamma, which is the fastest moving and the most penetrating, which means it's the most harmful for you. And if you'll notice, the alpha particle looks just like a helium nucleus. If you were to look at helium on the periodic table, you would see that the mass of it is 4, the atomic number is 2, and that tells you that it's helium. It's also abbreviated as a little a, like the alpha sign. And again, it talks about the charge and the mass here. We won't worry about that for right now. Same thing with the beta. The beta looks like it's like you're losing an electron. There is no mass, but there is a charge, and the charge is -1. Or you can use the symbol for the B for the Greek letter for beta. And again, electrons are extremely small, so they don't weigh too much, and it has a charge. And then the reason why the gamma are so penetrating is because there is no mass, there is no charge, so they literally move in and out as easily as possible and can penetrate just about anything with the exception of like lead and concrete. And a lot of it is explained here as well as to how the decay process works. But if you'll notice, what we did in class is... I'm sorry, I'm going to open this up so it's not as grainy. We talked about the actual equations themselves, and the equations are one side has to equal the other side. So when you look at it and you're looking at this problem, you will notice that the reason why I put the little fake equal sign, it's not really mean equal, okay? It really means yields. But for all intents and purposes, while you're learning it, if you just want to say one side equals the other side, it's just fine. So 206 is on one side, there's the arrow, and it's equals, and then you have 202 plus 4. Well, if you add those up, 202 plus 4 equals 206. And then the same thing over here. If you have 84 on the bottom, you should have 84 on the bottom on the other side, and you do. 82 plus 2 is 84. And then same goes for the concept down on the bottom. Doesn't matter what type of decay it is, the process is the same. So if you have 124 on the top on this side, you should have 124 on the top on the other side, which we do. 124 plus 0 is 124. Now here's the tricky one. Okay, electrons always throw in a little bit of a detail snag. You have 51 on the bottom on this side, which means you have to have 51 on the bottom on the other side. Well, if you already have 52, 52 minus 1 is 51. And then this will tell you that if you have a -1 on the bottom and 0 on the top for mass, it has to be a beta particle. And remember, they're here in case you don't recall what they look like. Alright, so because these came out of the process, that's a decay. And if it's 4,2A, or the 2 is the HE, you can write it either way, that means that this is an alpha particle that came out. Alpha particle looks like that. Whereas the beta particle looks like this, with 0 on the top, -1 like we just said. And if it's on the outside, coming out of the equation, it's decay, so it's a beta decay. Alright, so if you go on further, like I said, the answers are already here, but if we were to ignore these for the moment, and I'll do that really quick, just so you guys can see what it's supposed to look like. So if we were to do these, well, that didn't help. I thought it would be on the top instead. Sorry guys. Let me do this. 1 second. So I went ahead and just deleted all the answers so that you'd be able to do it on your own. And again, the whole key for this is in the classroom for key right there. So if we go back to this and we talk about what happened and what we're doing, you'll look at the equation again and you'll find where the arrow is. The arrow again basically means that what you start with, you must end with. So whatever's on one side has to equal the other side. So in this case, you have 129 on the top, and you only have 0 on the other side. So 0 plus what is going to give us 129? Well, for the top number, that should automatically tell your brain, okay, that's got to be 129 on the top. So we write 129. Then for the bottom number, okay, I'm just going to make this a little smaller because it's a little too large. Sorry, should be there. Make this 14, and let's do a different color so you guys can see the difference. So if it's going to be 129 on the top, you have a -1. Negative 1 plus what is going to give me 53. So -1 plus 54. So if we make this 54 minus 1 equals 53. And then we have to go to the periodic table and look up our element on the periodic table. So let's do that now. Go back to our week 8 information. You have a periodic table link still here. So if you click that and you go to the link, you're going to look for, again, the element is 54. So remember that bottom number is the atomic number. So that's going to tell you what element you're discussing. So look up 54 on the periodic table. If we go there, we would find 54. So notice 54 is xenon, Xe. So all you would do is write the Xe for the nuclear symbol. So if I go back to the right page, I'm going to make that Xe. And there's my answer. So if you add it all up, everything should add up, everything works out, and then my symbol is Xe because that's the element that the 54 represents. Okay, we did number 3 in class as well. And if I go here to number 3, we're going to do the exact same thing. It's just the weird thing is that it's now on the other side of the equation. Doesn't matter. This is still the decay process. We just want to know what's the symbol or what the element was to begin with. We now know that it decayed down to berkelium, but we want to know what was it in the beginning. So we do the exact same process. We say 239 plus 4 is, and that comes to 243, sorry. 243, so we would just enter 243, and then we say 97 plus 2, and if we do that, that's 99, and so 99, and now what we have to do is look up the element that's number 99 on the periodic table. So if we go back to the periodic table, we look up number 99, and notice, again, like I told you guys in class, here you would think that the numbers are here, but they're not. Those numbers from 99 and such are down here in the inner transition metals. And if you go through them, you'll find number 9 is Einsteinium. So you'd put ES in that place. So you would write ES, and now you're done. Now, if it were to ask you what types of decay these processes are, it does not. But if you wanted to know, and if it's something asks you later, like on the assignment that you're actually supposed to be doing today, you would look at this and you would say, okay, well look, this atom decayed to xenon and this particle right here. Well, what is that particle called? We said 0, -1 e. If you look back, 0, -1 e is a beta. So that is actually known as beta decay. So again, it's not asking you to do that in the assignment here, but if it does in the homework, then you need to be able to say that it is a beta decay. Alright, and then you'll look at this one and do the same thing. You're only looking for the right side of the equation at the moment, because those are our decays. And if you have Einsteinium, is decaying to berkelium and what else? A 4,2A or He, okay, and which would be an alpha particle. If you look here, 4,2, and then either the A or the He. So that is in what we call an alpha particle, or an alpha decay. So, alpha decay. All right, so now the only other thing that you can have, just like in math classes, is instead of having your answers already written out for you, we could put things into word problems. So we did number 12 in class, and all you have to do is really just rewrite this as to what it looks like. Instead of putting it in words, we put it in symbols. So that's what we're going to do right now. So protactinium 229. So if I were to write that, okay, I would do the symbol again, 229, because that's my mass, remember. That's going to be the difference between your isotopes. And then we have to look up what the atomic number is for protactinium. It might take you some time, and of course you can actually do, if you know it, the control find and look up protactinium, protac, and if you notice, it'll actually pull it up right there for you, and it's number 91. So I'm going to put number 91 at the bottom, and then we notice that the symbol, just in case you forgot, is Pa. So you go back and we put that Pa is protactinium. Now, yields or equals, right, in this case for the most part, it says 2 alpha decays. Well, remember, alpha decay was these guys, all right, so our 4,2-HEs. So I'm going to write it that way because it makes more sense to me, and I think it would to you too. So we're going to go ahead and put the 4,2-HEs here. All right, so I'm going to put 4, and then 2, and then HE. Now, notice it does say 2 alpha decays, which means you could actually put a 2 as a coefficient in front of this whole thing to symbolize that you have 2 of them, or you can just do what I'm about to do, which is just say the same thing twice, and then just do 4,2-HE. So 4, 2, and then HE, and then we're not done, of course, because now we still have to include francium here. So if we look up francium, we put francium in. The top number, the mass number, of course, is 221, so we're going to go ahead and put the 221. And then we have to look up francium, and I know where francium is because I know the periodic table fairly well. Francium is down here at number 87, so we use the atomic number 87 and place that into our equation. So the bottom number is going to be 87. 87, and then the symbol for francium is Fr. So now you have to go back and just check to make sure that you're not missing any particles, that for some reason in the equation they forgot to tell you something. So we just check to make sure our numbers are equal. And so 221 plus 4 is 225, plus 4 is 229. Check. Bottom numbers should equal 91. So 87 plus 2 is 89, plus 2 is 91. Check. And notice the atomic number for the 2, the 87, and the 91 all tell you what element they are. If it is not a number, if it's a negative or something like that, then that means you're dealing with a different kind of particle. And again, that can happen. You'll see it like a gamma ray decay, or you'll see a beta decay. You could also have a neutron. And if you have a 0, -1, that's a 1, 0 is a neutron. So if it looks like this, I'll put it up here just in case. It's called a neutron. And a neutron will have the symbol, sorry guys, I'm trying to get the video done before I run out of time, is going to be 1, sorry, let's use these, it's going to be 1, 0, and then it's going to be an N. So that's an actual neutron. Don't worry about this stuff for right now, but of course it's also charged as 0 because it's a neutron and they're neutral. But you can see neutrons, and you're going to find that when we talk about fission and fusion. So you'll actually use a neutron to start some of those processes, or it will come out in the end due to processes that are involved. If you have any other questions on anything, don't hesitate to ask, send me a message, or come into office hours. We'd love to see you guys Mondays, Tuesdays, Thursdays, and Fridays from 12:30 to 1:45. All right, guys, catch you later.